So, Alfonso, we are all yours. Thank you.
Okay, so good morning, everyone in Costa Rica. Good afternoon or evening in other places. So welcome to this third and last day of this session on geometry and topology. And our first speaker is Midory Komatsudani Quispe from University of Plymouth. She studied at Universidad Nacional Mayor in San Marcos in Lima, Peru. And she's also a master in mathematics at Universidad Federal de Rio de Janeiro and PhD from IMPA in Rio de Janeiro. She's working on holomorphic foliations, and let's hear her talk today.
Thank you. Is this fine?
Yes, we can hear you.
Okay.
Yes.
So,
Yes, we
okay. Can it be seen? Is everything all right?
Yes, we can see your presentation.
Okay. So we talk about the Bott indexes and one-dimensional foliations on the projective space. So I'm interested in the following map. If I have a foliation with a fixed cotangent bundle and I calculate the Bott indexes, I want to know what is the generic rank. So I will explain later why I'm interested in this problem. So for foliations on the complex projective plane, we have here an example. Here you have this vector field, which defines a degree 1 foliation on the complex projective plane. And we can see that it has 3 singular points. If we study the linear part, we see that it has the following eigenvalues. And if we calculate the Bott index, in this case will be the sum of the eigenvalues. We square that sum and we divide it by the product of the eigenvalues, we get these numbers. And if we sum up all, we get 9. And 9 can be seen as the square of 1 plus 2, where 1 is the degree of deflation. Another example, if we take this vector field, also defines a degree 1 foliation on the complex projective plane. And it also has these 3 singular points. If we see the eigenvalues, now they are complex numbers, and their Bott indexes are also complex. And if we sum up all the Bott indices, we have 9 again. So this is not a coincidence. This is given by a theorem due to Bott. So the Bott index formula on the projective plane, we have that if M is a compact complex surface and F is a foliation on that surface with only isolated singularities, then the sum of the Bott indexes and in all the singularities of the foliation is equal to the auto-intersection of the normal vector bundle, the cotangent bundle. If now the surface is a complex projective plane, then and F is a foliation of degree D, then the sum is D plus 2 all square. So we have a fixed number here for any foliation. And here the Bott index is the one that is related with the sum of the eigenvalues. So we have a formula for the Bott indexes here, for the sum of the Bott indexes. But we can ask if there are more, if there are other universal relations among the Bott indexes. So we had one, but are there others or not? We can study that by studying this map. We see the space of foliations on the complex projective plane of given degree, and we take a foliation and we calculate each Bott index at each singularity of the foliation. And to know how many universal relations, we will have to study the rank. For our example here, we have this vector field generates a folation, and its Bambuk indices are these numbers. So the image will be this three coordinate point, and the sum of the Bambuk instances by the theorem is 9, which we also calculated, and so every time we see that the image of this map is contained in the hyperplane given by the by this sum. So the sum of the coordinates, it lies in an hyperplane. So in general, we would like to know what is the generic rank. So the rank on the complex projective plane, it was calculated by Lins, Neto, and Pereira. And they say that if the degree is greater or equal than 2, then the generic rank of the Bambuk map for degree differentials on the complex projective plane is d squared plus d. In particular, they also have the dimension of the generic fiber, which is 3d plus 2. So the conclusion is that the Bott formula is just the only one relation among the Bott indexes on the complex projective plane. And if we want to generalize this concept, first let's review about elementary symmetric functions of the eigenvalues of a matrix. If we have a matrix, we can calculate this polynomial in terms of t times the identity matrix plus a. We get a polynomial here. The coefficients are called J's elementary symmetric function of the eigenvalues of an n times n matrix. For example, the first elementary symmetric function will be the trace of A, and the last one, the nth elementary symmetric function will be the product of, will be the determinant of the matrix. And I can denote, or I will denote this product with this multi-index that assigns to each elementary symmetric function exponent. So for example, if we have this matrix, its eigenvalues are 1, 2, and 5. So the trace will be just the sum of these of the eigenvalues. The second elementary symmetric function will be multiplying two eigenvalues, and then we sum up everything. And the third elementary symmetric function will be to calculate the determinant or the product of these eigenvalues. And just to give a concrete example here, if we have this multi-index 2, 1, 0, we assign to the square 2 to the trace the exponent 2 to the second elementary function 1, and to the third one just 0. Okay, and with this we can state the Bambuk theorem. So if M is a compact complex manifold of dimension n, and L is a holomorphic line bundle on the surface my manifold, I take an holomorphic section of the tensor product of the tangent bundle of M and the linear bundle L, which has only isolated singularities, and we consider the shared classes. Then we can calculate the shared classes of this tensor product just on the singularities of this holomorphic section. So, this this number does not depend on the holomorphic section. So if I can choose any holomorphic section that has isolated singularities, and I can calculate the shared classes. Here, this is this residue is called the Grothendieck residue symbol, and this one I to denote the Jacobian matrix. And also this number, we call it, this residue, we call it the Bott index nu of the holomorphic section at the singularity P. So for our Bott map, so we have a foliation and we have a singular point. We are going to choose the ones that are not non-degenerate, because at this point, the calculations are easier. We choose a germ of a vector field which defines the foliation around a singular point. If we have this multi-index, we ask this arithmetic condition. The first index plus 2 times the second index, and the last index multiplied by n, and the sum will be equal to n. Then the Baum index associated to the foliation to the multi-index alpha at the singular point P is given by this formula, where C alpha is the first elementary symmetric function, C2 the second elementary symmetric function, and Cn the nth elementary symmetric function. So for example, for n equal 3, we are interested in the Baum indexes associated to the first elementary symmetric function with exponent 3. The other index will be the first elementary function with a second elementary function, and the last one will be the third elementary symmetric function. For n equal 4, we have now 1, 2, 3, 4, 5 indexes that we are interested in. We can define 5 Baum indexes. So here we take C1, and the exponent of the first elementary index is decreased. To define the local Baum map, we take the space of foliations, which is generated, well, in this case, we can say that it's generated by some kind of, by some specific polynomial vector fields. The foliations that are reduced are the foliations which the singular points are non-degenerate. And n will be the number of singularities of any foliation here. In general, this is the nth Chern number of this tensor product. And we are going to take this multi-index such that they satisfy this condition. And I just enumerate them. Okay, I'm giving them just an enumeration. So I take a foliation that is reduced in the projective plane of degree d. We can have a neighbor inside this space of foliation of reduced foliations. We can define holomorphic maps that assign to each foliation at that neighborhood singular points. So the local Baum map will be for each foliation you assign the Baum indexes, these ones, that at each singular point, from the first one till the last one. So we can see that if we have an initial foliation here that is reduced, and we have the singular points, then we get holomorphic maps that assign to each foliation here is singular points. So we can define the local Baum map at each singular point. And the global Baum map will be just to symmetrize the coordinates, so we don't care about the order that we take for the singularities of the foliation. So to calculate the generic rank, we give first an upper bound for the rank. For degree 1 foliations, we have that the generic rank is n-1. For degree greater or equal than 2, if it's a complex projective plane, you get t squared plus t, which is the upper bound given by Alcides and Pereira. And if n is greater or equal than 3, then at most can be the dimension of the space of defoliations on the complex projective plane of the dimension n, and degree defoliations minus the dimension of the automorphisms on the complex projective plane of dimension n. And here we have the dimension of the space of foliations. So we have an upper bound here, and here we have the exact generic rank. So for the proof, we take just a fiber, a generic fiber. We denote GR, the generic rank, and n is a number of singularities. That dimension of generic fiber will be the dimension of the space of foliations minus the generic rank. And we look at the action of the automorphisms onto the space of foliations. And then the dimension of a generic orbit will be at most the dimension of a generic fiber of the map. And then we study stabilizer of the generic orbit. Depending on that, we get that for degree 1, we have that the generic rank can be at most n-1. And for the greater or equal than 2, the dimension of the space of foliations minus the dimension of the automorphisms. Because here and the stabilizer is just the identity, so that's why we get this. Also, we see that any Bott index depends on these n-1 indexes. And the Bott indexes, I mean, the Bott theorem gives us n-1 relation between these indexes. So we have another bound. We have this bound. And if we take the minimum, we get the result. So we get this upper bound. For the complex projective space of degree 3, we have that the upper bound is attained. So we have that the generic rank is the dimension of the space of foliations minus the dimension of the space of the automorphisms on the projective plane of dimension 3. But just for the degree 2 until 9. And why is that? Because I obtained the specific examples to show that. So for computed rank, we can think of the space of foliations, the tiny space of foliations generated by these vector fields. So to compute the derivative of the Bott map on a foliation, or we can say also a vector field, is just to take this space and calculate at each singular point the derivative of the Bott index. So for, as I told you, for the specific case of the complex projective plane of degree 3, this vector field makes the bounds I obtained the upper bound. The upper bound is the one given by this foliation, and a similar vector fields with degree 4 until 9. They also have that their rank of the Bott map is equal to the upper bound. For degree 2, and I have this homogeneous vector field that defines a foliation on P3 at degree 2. It also have the rank of the derivative of the Bott map. It's also the upper bound that I gave before. So this works for P3 and also for P4. Similarly, we also have another vector field that also works for the case of P4. And I also studied the general foliation. And what is good about the general foliation? So in homogeneous coordinates, the general foliation can be given by this vector field. And in affine coordinates, we can see it like this. Okay, this vector field in CN. It has two automorphisms that lives invariant defoliation. What helps, so they are helpful because to calculate the Bott indexes of the general foliation, we just concentrate on one singular point because this permutes the singular points of the general foliation. And this one, we just concentrate on not in the whole space of vector fields, just in one part. So that's the reason why we like to we want to study this automorphism. So when we study the general foliation, we obtain the Bott indexes, and they are exactly, they depend on D and N, and in particular for any foliation that has isolated singularities, the sum of these Bott indexes will be this number because it doesn't depend on the foliation. Well, the result is given by the Bott theorem. And the rank of the local Bott map at the general foliation, it can be given in terms of D and N and some matrices. Here, where this AG are some specific space of vector fields that depend also on N and D. So they depend on N and D. That's what all I want to say about the rank of the Bott map at the general foliation. So and to be more specific, if we see the general foliation of degree 2, we obtain that it's generic. We obtain that the rank at the Bott map at the general foliation is this number. So we had an upper bound, and now the general foliation attains the upper bound. So in general, we have that the rank of the local Bott map is this upper bound, the upper bound given before. And what happens on P3? So unfortunately, the rank is less than the upper bound, but we still can calculate the rank of the local Bott map at the general foliation. And so just to summarize, the result is the generic rank of the Bott map that goes from the space of foliations of the projective plane of dimension n, degree D foliations. We assign to each foliation its Bott indexes at each singular point. Then for degree 1, we know that is n minus 1, the generic rank. For degree 2, and so on, for the projective plane is D squared plus D. The result was given by Alcides Neto and Pereira. For dimension 3, degree 2 until 9 are given by the examples that I showed before. And for for projective plane that has a even dimension and degree 2, the generic rank is given by this number. And outside that, we know that it can be at most this difference, no? The dimension of the space of deflations minus the dimension of the dimension of the automorphism of the projective plane. So we had the index, some relations given by the Bott theorem. And with this, we see that there are other relations that we don't know that relate to these Bott indexes. So thank you.
Thank you, Midori. Thank you for your talk. So is there any question, comment? Well, if not, let's thank Midori for the talk.
Thank you, Midori.
So now we have a recess until 10 o'clock in Costa Rica.
I think it is, yes. So,
Alberto raised his hand, or oh, okay, or he was clapping. Okay.
It was a one-hand clap like this.
All right, all right. So let's go for the recess, and we'll resume at 10 o'clock.
good.
Okay, thank you, Midori.
Thank you,
Nice
Midori.
talk.
Thank you.
Komatsu.
Thank you for the invitation. Bye bye.